Given a circle with radius r, we can say that sine of theta, the angle measure, is equal to y over r, and cosine of theta is equal to x over r, where theta is the angle measure and xy is a point on the circle. We can even make this simpler by considering just the inputs and the outputs of these functions. So sine can be represented by y equals sine of x, and cosine can be represented by y equals cosine of x, where x is a real number that represents the angle measure, and y represents their output. But for this video and for future videos, we will be using the general form of these two trig functions. Now they might seem a lot more complicated, however, they make graphing these trig functions a lot easier. This is what the general form of our sine function looks like. Notice how we have many more variables floating around now. We have 4 of them, a, b, c, and d, and each one of these helps play a role in graphing the function. But before we talk about that, I want to show how to go from a standard form of our sine functions to a general form. Here's an example. Y equals sine of x. This can be rewritten in general form if we let a equal 1, b equal 1, c equals 0, and d equals 0. Now we want to show that these two sentences are equal to each other. So I'm going to simplify the last line. 1 times anything is itself, so we can get rid of that red 1. Similarly, 1 times anything is itself, so we can get rid of that yellow 1. Anything plus 0 is just itself, so we can get rid of that green 0. And lastly, anything plus 0 is itself, so we can get rid of that purple 0. So there we go, we proved that these two statements are the same. In the upper left corner here, we have cosine's general form. Notice how it has the same 4 variables that the general form of sine had. It had a, b, c, and d. For our next example, we're going to have y equals cosine of 3x plus 6 plus 1. Our goal here is to rewrite this into general form. Now it might already look very similar, however we're missing a couple of things. The first thing is that we want to establish what a is. And secondly, notice how in the general form there's a parentheses inside the parentheses. Currently, we don't have such a thing, so our goal is to make a parentheses inside the parentheses occur. If we try to match our current function to look more like the general function, it will look like this. Notice how now we have a equaling 1 and we have a parentheses inside the parentheses. In order to achieve that, we had to factor out a 3. This 3 that we factored out is b. This process of factoring out the 3, or a number inside the parentheses, is very often used. So beware to keep your eye out for that. Alright, so now let's talk about what each one of these letters represent. A is the amplitude, so it's how far my graph stretches from its center line. For example, if a is equal to 3, then my graph stretches a factor of 3 from the center line. The period is the length it takes for my graph to complete one full cycle. So b is not the period, but it leads to the period. I can calculate the period by taking 2 pi and dividing it by the absolute value of b. So how does b affect our graph? Well, normally it takes a length of 2 pi for our trig functions to complete one full cycle. If b was equal to 3, then it would only take a distance of 2 pi over 3 to complete one full cycle. So, in a sense, it shortens the wave. D represents the vertical shift, which is how many units up or down our graph is translated. For example, if d was equal to 3, then our entire graph shifts up by 3 units. Notice how the normal starting point is at 0, 0. Now the new starting point is at 0, 3. C represents the horizontal shift or the phase shift. So for example, if C was plus pi, it would move our entire graph over to the left by pi units. If C was minus pi, it would shift our graph to the right by pi units. If you take a step back, you realize that we've been doing this all semester long. Transformations are nothing new to us. We've been doing them with parabolas, cubic functions, absolute value functions, and even the square root function. So don't get scared by all this notation. It's nothing you haven't done or have already seen before. Also note that all these transformations are also the same for the cosine function.